Here we are, part two, error propagation. I actually love this topic, partly because this was something that was always very magical to me as a student, and not magical in the sense of, wow, this is wonderful. Magic in the sense of, this is some dark art that I couldn't possibly comprehend. And then one day I had to teach it. And so I sat down and figured it out. And I was like, oh, that's actually not that bad. Why didn't anyone ever explain this to me like it really is? So I'm going to try to do that for you today. Reminder, error is distance. It is how far away you are from the true value of a quantity with your measurement or with your calculation. Now, just in case you've forgotten high school algebra or geometry or whatever you want to call this, the distance formula, right? Pythagorean theorem, call it what you will. Was it actually Pythagoras' theorem or did someone else figure it out first? What an interesting question. I'm not going to answer that today. But what I will say is that I want you to remember that the distance formula doesn't just apply in 2 dimensions or three, it applies in any number of dimensions. If you have 16 coordinates, then your total distance is coordinate one squared plus the second squared plus the third squared plus the fourth squared, blah, 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 gives you the distance squared. And you're like, why is he talking about multidimensional spaces? Because error is a distance and it lives in a space of all of the different variables that you're measuring. So if you have 16 different variables in your experiment, first, I pity you. And second, you need to know how to deal with all of those different variables and all those different sources of error. So that's what we're building up to. Okay. As long as I'm starting to get off topic before I get on topic, let me just unload for a minute here. So, make yourself some tea or whatever. Come right back though. Uh, the thing is that first we have to get through this inhibition that people have about the word error when doing science. Because in casual, vernacular, everyday English, error usually means mistake. It means you did something wrong, it means you messed up. And that is simply not what the scientific meaning of the word is. It doesn't mean that the regular everyday English usage is wrong. It means that these are two different flavors of the English language and that this word has very distinct meaning depending on the context it's used in. So, an error in science is not a mistake, it is unavoidable uncertainty in a quantity. Or maybe it is avoidable known uncertainty in a quantity, but it doesn't necessarily mean, and it probably doesn't mean you did anything wrong. If anything, it means you did something right because you noticed this source of uncertainty and you quantified it so you can do something about it so that you can actually correct for errors to get closer to the truth with higher confidence. So, error is not a bad thing, quite the opposite. Studying error makes us better at what we do. Great. I feel better. No, actually, I don't feel better. I need to get this off my chest too. So, part of this is like my trauma from teaching high school science, but it's also trauma from inheriting students who have taken high school science with teachers who are not me. I'm not trying to pretend that I'm the best in the world. That's just objectively not true. But on this topic, I have very strong feelings, and that is that using human error in your lab reports is absolute garbage, and you should not pull that nonsense. Now that I've said how I really feel, let me explain what I am saying because there really is rigor and logic here. And it actually comes back to vocabulary. Human error has a very defined and very important meaning in engineer. Human error means a human being made a mistake in a decision. It means that they executed on an idea or a plan incorrectly, or that they made a poor choice and that there are consequences of that choice. That's what human error is. It doesn't have anything to do with the limitations of human sensory apparatus. Like if you're trying to read a ruler and you're like, oh, maybe I read the ruler wrong. That's not human error. That's called reading the ruler wrong. If you are doing a microscopy analysis and you're analyzing an image visually, like a micrograph of the microstructure of some material, there are limitations to what your eyes can perceive. That's not human error, that's just sensory limitations. Human error is mistakes, it is bad decisions, it is failed execution that's different from the fact that we're humans and so we just aren't infinitely precise. Okay, I feel so much better. But wait there no, okay, that's enough for today. We can have more rants another day. Let's get back to work. Oh, long story short, if you are actually talking about human error in an engineering report, absolutely use that phrase, but use it when it's appropriate and don't use it when you should mean something else. Okay, great. Back to work. So, any experiment that we perform, any calculation that we perform is not infinitely precise. There's always some plus or minus. This is unavoidable. This is just the nature of the physical world. What makes this a challenge is that when we go to measure things in the lab or in a simulation, that we very rarely have the luxury of directly measuring the variable we actually care about. Let me give an example. In material science, studying crystal structures of materials is really, really important. And so, what we want to know is all of the distances between all of the atoms in that crystal. That's the quantity we desire, is the distance d. But the problem is, you can't measure that directly. You can't like go in there with your tiny little nanoscopic calipers and like put your calipers on the little atoms. This is already getting ridiculous, right? Like you just can't directly measure the interatomic spacing. But what you can do is shine X rays through that crystal, measure the angles that they diffract at, and then calculate the atomic spacings based on the diffraction angles. So we calculate what we want to know from what we can actually measure because you can measure an angle directly. You put a protractor up to a thing and you're like, it's that many degrees, that's the angle. That's a direct measurement. So, what we need to learn today, now that I'm 7 minutes into this video, sorry for the long warm up, is how do we perform this mathematically? How do we say, I want to know X, I had to measure Y and calculate X, what's the error calculation look like? We are doing single variable today. So, maybe I label my variables backward, doesn't matter. Here's the formula. We want to know Y. We are measuring X. So we measure X, we calculate Y. X has some error in it. That's delta X. So the error in X squared times this derivative. How strongly the calculated quantity depends on the measured quantity. I hope intuitively that actually makes some sense when I say it this way. If you're like, wow, my diffraction angle is really strongly affected by the interatomic spacing, that derivative is really big. The rate of change of one with respect to the other is a large quantity, which means small errors in the one drive big errors in the other. That's why we're differentiating and multiplying here. And if that didn't make sense, talk to me in class. We'll get there. So this is our formula. This is it. This is the magic. Like this is the whole lesson. If you're content with this and you're like, cool, makes sense, I got it. See you next time. If you would like an example, then let's do that. Now, I will admit this is a little bit made up because as I said, we're starting with single variable because you should start simple and then get more complicated. But most problems in real life are not single variable problems. That's just how it be, you know? So I admit this is a little fake, but it will show the method. So we are going to estimate the diameter of a copper wire in order to estimate the resistance of that wire. So here's our formula. If you've forgotten it from Physics 240, resistance depends on resistivity, wire length, and wire area. I am not going to unpack I don't know that I have Physics 240 trauma, but I'm definitely salty about it still 23 years later. So, story for another time. Okay, on topic here. We can do this. Resistance depends on resistivity. That is an intrinsic material property that is already known very precisely. And in this pretend example, we're going to say that we also know the length very precisely. In reality, we'd have two sources of error, both the diameter and the length, and we'd have to do more math, but not today. So we express our desired quantity R in terms of the measured quantity D. And now we have this expression. So again, just to be really explicit here in this problem setup, all of these things, 4 is a constant. Rho, the resistivity, is a constant. L is treated as a constant. It's something we know very, very precisely. Pi is a constant. Our variable is the diameter D. So the error in the diameter drives the error in the resistance estimate. So we have to take a derivative to see how strongly the resistance depends on the diameter. So we take a derivative. Here it is. You just use power rule, pull out the power, and here's our formula. Now it is time to plug in numbers. So here's the real values. This is the resistivity of copper. Here's the length of my made up wire. And then here's the diameter of my made up wire. Note the reporting here with this plus or minus. So I'm saying the average, the mean value of the diameter is 2 millimeters, but the uncertainty in that diameter is 0.5 millimeters. So I'm saying really here, the diameter is somewhere between 1.5 and 2.5 millimeters. I don't know where exactly in that range it is, but 2 is the middle of the range. That's what we're doing here. And now we plug in those numbers. So we put the values into our derivative that was calculated on the previous slide, do some multiplication and division. This is what pops out. This is the rate of change of the resistance if the diameter is estimated a little bit high or a little bit too low. Once we have that, then we are going to take that value of the derivative, use it to calculate the error in the resistance. So we take a square root. These will be absolute values. We're getting the plus or minus in either direction on the resistance. We put in our numbers from the previous problem. Note that this 0.005 meters is our plus or minus half millimeter uncertainty in the diameter. And we multiply and we get an uncertainty in the resistance, plus or minus 8 milliohms. So we have our numbers and you go to report these things. We have the value of the resistance, 4 rho L over pi d squared. And then we have the uncertainty in the resistance, delta R. And so it's, again, the average value plus or minus uncertainty. Crank some numbers, do a little bit more multiplying and dividing, and we land with all this. This is the final answer. Notice that the error has the same units as the quantity itself. This is a check you can do if you need to check your work. The units should line up. The resistance is in ohms. The error in the resistance also is in ohms. Great. That's an example problem. I know I went through that a little bit fast. Mostly it's multiplying and dividing numbers. I just didn't want to say a bunch of multiplications. Feel free to slow it down, watch it again, or, come ask me in class also. Now, I've mentioned that in the real world, we usually don't have a single variable and we usually have more than one source of error. And if you are thinking well, you teased that whole distance formula thing and you kept talking about multi-dimensional whatever, can I just square and add everything and be sum my squares of the individual errors to get the total squared error? That is a very good guess. It just happens to be wrong. It is a very, very reasonable guess. But each of these errors has a different coefficient on it that is given to us by how strongly the final result depends on that particular source of error, because different sources of error can have different levels of importance in an experiment. And so these coefficients help us weight them. You're like, how do we calculate the coefficients? Stay tuned. That's not going to be the next day, but later in the semester when we do some multivariable calculus, we can come back to this. All right. Before I wrap it up today, I always need to say, why do we care? Well, my beginning of lecture rant aside, which was absolutely true, and I stand by it, but you simply cannot eliminate error entirely. It's always present. You have to be prepared to deal with it if you're going to do good, justifiable, defensible work where you can say, not only, here's the number I got, but here's my uncertainty in that number, and here's how confident I am that my answer is representative of the true value. That level of rigor, unfortunately, is not always met. And so by doing that, you set yourself apart. Furthermore, I heard this as an engineering major. Some of you may actually go and get real jobs where you really design and build real things, which is great. I love it. And in a manufacturing process, there is variability. So, all of these concepts of uncertainty and allowed ranges, and how much does my final answer change when my ingredients change? These are very, very tightly linked to problems of quality control and quality assurance in manufacturing. And saying, yeah, I'm going to make my car out of this sheet metal and it is going to be stamped with a curvature of some radius, that's not infinitely precise. That's going to vary a little bit from one car to the next. And that variance in the curvature from one car to the next affects stress concentrations, which affects safety factors like how big of an impact can this withstand. And so you need to be able to proactively take this into account when you're making designs and saying, hey, the curvature in this car part is going to be plus or minus so much. Now I know how to do the math to say this leads to plus or minus in the experienced stress in a collision based on the geometry, which means that I can trust that this part will not fail under a certain load, even though some of them aren't quite as good as others. And that's really, I think, the end goal of all of this from an engineering point of view is to make designs that are more robust because you know how to account for variability in the process of manufacturing those designs and making them reality. So, yeah, this is important in science. Truly. I mean, I'm not saying that to minimize it, but it is not purely a matter of like scientific discovery and hypothesis testing. This is across the whole spectrum of problems where variation is just part of the process. So, there you go. That's everything I have to say. And thank you for either politely ignoring or even better yet, actually listening to my rants and opinions. And with that, I suppose I will sign out and say, see you in class.